Hi everyone, this video is on Caley's theorem. It states every group is isomorphic to a group of permutations. This theorem is considered as a classic of group theory, and what a discovery this theorem is, what a generalization this theorem is. To every group, its structure can be found in some group of permutations. Every group, its structure lies in some group of permutations. So what a discovery it is. Next we proceed to its proof. We prove this theorem by showing a group G is isomorphic to a subgroup of Sg. Here Sg is a group of permutations of G. So a subgroup of Sg is also a group of permutation, and we show the group G is isomorphic to a subgroup of Sg. Now we consider the elements of the subgroup of Sg. Consider a function from G to G, a function lambda x from G to G, such that lambda x of G is xg for all G belongs to G. Then consider lambda x of A equals to lambda x of B. That gives us x equals to xb, and that gives us a equals to b by the left cancellation law. This shows lambda x is one-to-one function. Consider C belongs to G. Then for any C belongs to G, we have lambda x of x inverse C equals to x inverse C, that equals to C by application of associativity property, and this shows lambda x is onto. Lambda x from G to G is both one-to-one and onto, that is lambda x is bijective, therefore lambda x is a permutation of G, so lambda x belongs in Sg. Now to show G is isomorphic to a subgroup of Sg, we find an isomorphism from G to a subgroup of Sg. For that, consider a relation phi from G to Sg such that phi of x equals to lambda x for all x belongs to G. X belongs to G and lambda x belongs to Sg. Then the set of lambda x for all x belongs to G is the required subgroup. Next, we consider phi of x equals to phi of y, that is lambda x equals to lambda y. That implies xe equals to ye because E belongs to G, and this gives us x equals to y from left cancellation law. This shows phi is one-to-one, and from the definition of this subgroup, it is clear that phi maps G onto to this subgroup, so phi is onto. Next, consider lambda xy of G, that equals to xyg from the definition of lambda, and that equals to x times yg by the application of associative property, and this gives us lambda x of lambda y g. This shows that lambda xy equals to lambda x lambda y. This is relation 1. Now we have phi of xy equals to lambda xy from our definition of phi, and lambda xy equals to lambda x lambda y from relation 1. Therefore we have phi of xy equals to phi of x phi of y, and this shows phi is an isomorphism from G to this subgroup of Sg. Therefore we have found an isomorphism from G to a subgroup of Sg, so G is isomorphic to this subgroup of Sg, which is a group of permutations, and we have proved the theorem of Caley's theorem. Hi everyone, this video is on a theorem of group of permutations. It states every permutation sigma of a finite set is a product of disjoint cycles. Proof: let sigma be a permutation of set A and let beta 1 dot 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 beta r be the orbits of sigma. Then to every orbit there associates a cycle. So to the orbit beta I there associates a cycle mu I such that mu I x equals to sigma x if x belongs to this orbit beta I, otherwise mu I x equals to x. Now we know that the orbits of a permutation of a set are the equivalence classes. So they define a partition on the given set. Therefore, the cycles that are associated with the orbits are disjoint cycles. They are disjoint. Now consider this product. Since the cycles are also permutations, they can be multiplied. So consider this product of all the cycles that are associated with the orbits of sigma. Now consider any element of A, x belongs to A, then x belongs to one of these orbits of sigma, and only one of the orbits of sigma, because orbits are equivalence classes. Now operate x by this product, we get sigma x. Product of this product times x equals to sigma x, because x belongs to only one of the orbit. Let that orbit is beta I, then this x is moved by only one of these cycles, mu I, and from the definition of mu I we have mu I times x equals to sigma x if x belongs to beta I, and for the rest of the cycles it does not affect. Therefore the product times x equals to sigma x, and we have sigma equals to the product of these disjoint cycles, and we have proved the theorem.